Hi everyone, so thanks a lot to the organizers for the invitation. The opportunity to kick off this workshop. This is my first time here. It looks like a really super nice place. Okay, so I will talk about the report on some story we have been developing with my colleague Johansson at KTH for a couple of years now, actually. So there are two parts. Two papers that I will try to describe. The first one is joined with Kurt, but the second one, which is we put on the archive just maybe 2 weeks ago, was joined with Courteaut. Okay, so I mean, maybe I should say from the start that this, even though somehow the problem setting for these two parts is quite similar, and there are objects that you can see that appear in both, still the actual structure of the problem is somehow at the end of the day quite different. I'm trying to bring this a bit closer project ahead, so if people have ideas for this, I would be happy to discuss. Okay, so here's the setting for the first part. So D will be maybe let me point. So D is a simply connected domain in the complex plane. It's a Jordan domain, and gamma is a boundary. So at this point, I'm not making any assumptions about boundary regularities. This could be a fractal curve, gamma, like this. It's like a snowflake. Then my main object of interest is this function, or this number associated to the domain, which I call the Coulomb gas partition function. So it's just, in some sense, a very simple thing. It's just this integral. And well, if you unwrap what is integrand, you see that it's just the product of the pairwise distances between these points, z, k, z, l, to the power beta over 2. And well, the log of this guy is called the free energy, and there's also a natural probability measure associated to this, where the density is just the integrand. Yes.
The over 2 is because of overcounting?
Yes. I could have taken just k strictly smaller than L. Right, this is some convention. So one way to think about this is as the partition function of a statistical mechanics model of n charged particles that are confined to sit inside the domain D, and they're interacting through this electrostatic energy. So this explains why I wrote it in this sort of complicated way. I mean, think about this as really as a statistical mechanics model. It's very natural. I mean, we will see that electrostatics somehow plays an important role in this problem. Okay, so integrals of this type appear in a lot of different contexts. For instance, random matrix theory, conformal field theory, random geometry, and so on. So we will see a little bit later. So this, okay, so we have this beta, which acts as an inverse temperature. If you think about this as a statistical mechanics model, for most of the talk, I will assume that beta is equal to 2, which is special, because in this case, the model is determinantal. So in that case, the partition function can actually be written as a determinant like this. And this is really important for the first part of the talk. It's not important at all, actually, for the second part. But for the first part, this is really a sort of critical assumption. Okay. So just to give a little bit of context, this problem of studying Coulomb gas in the plane, I mean, this has been studied for a long time. Part of the motivation comes from random matrix theory and so on. I mean, but the typical setting is a little bit different from the one I consider. So I would say the most common setting is that the domain D is taken to be the whole complex plane. In this case, you have a problem with integrability, so you have to put in some confining potential. And then, if one studies the probability measure, you try to let the number of particles go to infinity, and what happens if your potential grows fast enough is that the particles will sort of go to condensate on some set, which is usually called a droplet. And then the game is to try to describe this and maybe study various questions about statistics of the points, maybe in the bulk, on the boundary, and so on. Again, part of the motivation for this could come from the fact that choosing your potential wisely, these points may have the same law as the eigenvalues of some random matrix ensemble, for instance. In our setting, we instead fix the domain. So in some sense, we fix the droplet, and we force our points to be confined there. Of course, you could think of this also in terms of having a potential that's just equal to plus infinity outside your droplet, your prescribed set, and 0 inside. So our point of view, or our main problem, what we want to understand, is how this free energy, or how the partition function depends on the geometry of on the shape of the droplet that we prescribe. So borrowing terminology from Schiffer, we could say that we view this free energy as a domain function. So it's some number which depends on our domain, and we're interested in how it varies, or how it depends. Well, in general, I mean, you cannot, if you have a generic domain, you cannot really expect to be able to say anything sort of at the finite n. And so what we will do is study the expansion in the many particle limit as n goes to infinity and try to see this. Okay. So an important tool for me is something called the Grunsky operator. This will appear in both parts of the talk. So here is the setup for this. So I have my simply connected domain D. The exterior is called D star. Then I have the unit disk, blackboard D. D star is the exterior disk. Then there's a conformal map from the exterior disk to the exterior of my simply connected domain, D, by the Riemann mapping theorem. And if I expand it to infinity, it will have an expansion like that. So R infinity is the capacity of the domain. Then, and there are coefficients. Then the Grunsky coefficients are defined by taking the log of the difference ratio, like that, and then expanding. So I evaluate this guy at points C and W in the exterior disk. Then, because G is a univalent function, there's no problem in defining this logarithm, and this is an analytic function in both variables. So I can make an expansion, and I have some coefficients, AKL. Okay? These are called the Grunsky coefficients, and were introduced by Grunsky, I guess almost 100 years ago. Actually, in the context of finding criteria for whether or not the function is univalent, but in our setting, by assumption, it's univalent. Then I will do the following. So I take these guys, these AKLs, I will multiply them by root KL. This gives me BKLs, some numbers. I'll collect these numbers in a semi-infinite matrix, capital B. Okay, this you can do, of course. But then I will do something a bit funny. So I will think about this B. This turns out to be a good idea, to think of this as an operator acting on little L2. And the way it's doing this is just sort of by formal matrix multiplication. In a very simple way. Okay, so why would you do this? Well, maybe the first an indication that something interesting is going on is the original result of Grunsky, which is that this operator is actually a contraction on little L2. So this was proved. It's not hard to prove. You can get this basically from the area theorem. Okay. So of course, this Grunsky matrix B, or this Grunsky operator, it knows a lot about the simply connected domain, right? Because it has all the coefficients, and if you have the coefficients, you can figure out, if you evaluate the left-hand side on the diagonal, you get log of G prime. So these Grunsky coefficients, they know all there is to know about your domain, right? Because from it you can read off what is G prime. You can integrate and get back G. But what still after thinking about these problems for a couple of years, we find sort of remarkable is that even though that is a clear fact that you can read off anything you like from B, why would it sort of organize? I mean, how maybe not so easy to somehow extract this. Even if you know for a conformal map, if you know all the coefficients, it's not so easy to somehow deduce properties of your domain, find properties just knowing the coefficient. Nevertheless, it turns out for this problem that in many instances, several instances at least, natural geometric properties of the boundary of your domain actually corresponds to natural properties of the operator B. It's really viewed as an operator. So here are two examples. Gamma, the boundary of your domain, is a quasi-circle, meaning it's the image of the unit circle under quasi-conformal homeomorphism of the whole plane. Okay? This happens if and only if the Grunsky operator B is a strict contraction, meaning there is a kappa strictly smaller than 1 such that this estimate holds. This kappa, for those of you who know, this kappa is also quantitatively related to the dilatation of the quasi-circle, so the sort of roughness of the quasi-circle. This is not so obvious when you just look at the problem from the start. This has been known for, this is on some level known, I think, to Berling and Orfors in some direction. Certainly Pomer. So the second example, there are things in between here, but we can look at, quasi-circles can be quite rough, so they can have dimension arbitrarily close to 2, and they are also very important for various reasons. They appear in dynamics, in Teichmüller theory, and so on. But there's a very interesting subclass of quasi-circle, which can also be characterized by the Grunsky operator. So these are called the Weil-Peterson quasi-circles, and well, gamma is Weil-Peterson if and only if B is Hilbert-Schmidt. And so this class of quasi-circle is very interesting. There are many, actually, a lot of different characterizations, both geometric and analytic. There's a paper of Chris Bishop a couple of years ago that gives several different equivalent characterizations. But the reason I'm interested in this is, well, as you will see, there's a connection to the Coulomb gas, but I was interested in this class before, thanks to the work of Elin, because this class of Weil-Peterson quasi-circle is exactly the class of Jordan curve with finite Loewner energy. And I will define the Loewner energy as this, if B is Hilbert-Schmidt, then BB star is trace class. You can define this Fredrik determinant. Okay. No, the determinant in the identity minus BB star. And the Loewner energy I will define just as this number. That's not the original definition of Elin, but so I won't really talk about the Loewner energy and all the connections, beautiful connections to random geometry, to SED curves. Maybe I just mentioned that it's some number that appear, for those who haven't seen it, it's somehow the action function or the large deviation rate function for SED kappa, as kappa goes to 0. That's one way to see it. But it also provides a link between random geometry and Teichmüller theory. And as we will see, it also appears somehow naturally in the context of Coulomb gas. Okay, so let me just flash this slide. So I mentioned that there are a bunch of different characterizations, also different ways to compute the Loewner energy. I will refer to this later. This second line here that computes the energy, this Fredrik determinant, non-Fredrik determinant, in terms of Dirichlet integrals of the conformal maps from the inside of the disk to the inside of the domain and the outside of the disk to the outside of the domain. Although I won't use it, but in the smooth setting, if the boundary is smooth of your domain, you can also write this in terms of spectral determinant. I just flashed this. Okay, so now we come back to the problem. So remember that D is any Jordan domain, and I assume that my inverse temperature beta is equal to 2. Then okay, so I'm interested in describing the free energy, and it's convenient to somehow describe in some sense, the relative energy. So this Zn at unit disk, this is something that's computable explicitly. I will give the formula just from the determinant formula. We have a lot of orthogonalities we can just compute. So this log of the relative partition function, well, the first term is basically, if you think a little bit about the problem, this is sort of the first thing you would expect in some sense. So, because the capacity and the relation to the equilibrium measure, static equilibrium measure. Okay, so this term is somehow not so hard to get. You could view it as a scaling term if you want. You can see it from the scaling properties of the integral, the Coulomb gas integral. But then the second term is the interesting one. So you have a log of a determinant where we don't have this so B is the Grunsky operator for Grunsky matrix for my domain D, but then I truncate it. So Pn is projection on the n first coordinates in little n2. So this is now a matrix, and so these are the first two terms, but these are actually all the terms. So this is now an identity. So so if you compute the first, the partition function for the disk is just equal to that. But we see from the formula that we can actually view this free energy of the confined Coulomb gas as a kind of truncated or discretized Loewner energy. Because if I remove this projection, I get exactly, well, minus 1 over 12 times the Loewner energy on the right. Yes?
Is the B star over the trace class?
Yes. B is Hilbert-Schmidt, so B star is trace class.
So here D is just a Jordan domain.
No, of course, yes. So you're absolutely right. This makes sense for any Jordan domain, but if the curve is Weil-Peterson, then it would be trace class.
Oh.
Yes. No, this makes sense, but you make a truncation here with some. So this is true for any Jordan domain. But then if you want to take a limit like this, then you have to have a Weil-Peterson. Yeah, that's a good way. So corollary, this also gives me a new characterization of Weil-Peterson quasi-circles. If I have a Jordan domain D, then the boundary is a Weil-Peterson curve, if and only if basically this constant term here is second term is bounded. I just draw it like this to normalize. In this case, the limit exists, and it equals the Loewner energy of the boundary. Okay. But what is not so, I mean, the reason also I wanted to show these spectral determinants and so on is that it's not, we know somehow, at least in this case, when the boundary is Weil-Peterson, we also know that this limiting object can be also written, for instance, in terms of these Z-regular determinants. Here we instead have this Freedom determinant. Understanding more directly this link would be very good. Okay, maybe if I have time, I could come back to the proof, but actually it's not, proving this is not very hard if I do it in the correct way. So the idea is to use the determinant formula, and then, okay, if you have such a, you can do row and column operations and change to use other polynomials instead of the monomials that we had in the formula. Right? So you could, for instance, use let's say orthogonal polynomials for your domain and get some kind of expression. But then the problem is that we don't know anything about orthogonal polynomials for a given domain in general. So there's nothing to give you anything. But instead, what we are using is something called the Faber polynomials. Which are not orthogonal, but that somehow, in some sense, behave a bit like orthogonal polynomials, and they also play very well with the Grunsky operator. So there's some kind of identities. And actually, the required computations, although done in a very different context, are basically contained the work of Tachan and Theo, although they have a very different perspective. Okay, so there are, so now with this theorem we understand very well the behavior, at least in the way Peterson set it, when beta is equal to 2. Okay, so then we know that the expansion looks like that. We see the Loewner energy plus the little 1 term. But what happens when beta is different from 2? Let's say, but still positive. So we expect, and I will come back to this, maybe by comparison with another problem that we can do for general beta. We expect there to also be another term that, that depends on beta. It's some kind of energy like quantity, but it's multiplied by a constant that depends on beta. That one expects to somehow dominate when beta goes to plus infinity. But you could study the problem to sort of figure out what this constant should be, or this energy should be. You could try to think about the problem for large beta, or for beta equals plus infinity, so a completely frozen setting. This is actually a very interesting problem as well. This you have to interpret, but it should correspond to the distribution of Fekete points on the boundary. So these are just the points that minimize the electrostatic energy. So they will sit on the boundary. This is a classical fact. I mean, you could also view it just as the set of n-tuple points that maximize this discriminant. And well, it doesn't have to be unique and so on, as it's easily seen on the circle, for instance. Then, okay, and it's also very well known, classical result, that if you take like the 1 over n times n plus first root of this converges to the capacitor. But this is a really remarkable result due to Pomerenke from the 60s that actually computes the free energy of this. So somehow this is what I said. This is a leading term, which is easy. Here you have well, this is like n log n, but then there is a constant term, which is very closely related to the Loewner energy. So it's essentially so you have your curve, and then you have the conformal map that goes back to the exterior disk, so G inverse. Okay, you take a log of G prime of that. That's a harmonic function in the exterior of the curve. Okay, you take that guy, and you look at what are the boundary values on the curve. Okay, and then you take the harmonic extension of those boundary values inside the curve. Okay. That gives you a function that's harmonic away from the curve in the whole thing, and then you compute the Dirichlet energy of that. That's so you can write this in terms of normal jump operator. Okay, but this should hold if and only if gamma is by Peterson. This number is also finite. I just want to, I mean, some of this is a sequence of papers by Pomerenke that I think are really remarkable and actually sort of important for our story as well, at least in terms of techniques. Yes.
So is there a reason that the +1 changed into -1 in this n times n minus 1 factor? It was an n times n plus 1.
Yeah, so, right, so in some sense, I don't know, I mean,
some scaling addition.
yeah, so you don't have an integral anymore, so you pick up this extra thing somehow from the Jacobians. I don't know, that's some computation, but maybe there is a more intuitive way to see it. But this term is really classical. This is in the all-force conformal invariance book, for example. But here you have some monotonicity, which means it's not so hard. But this is a very interesting problem, but it's somehow very hard, because you have actually almost there's very little to work with. There's only the fact that they maximize this guy. It's like the only information you have. And there's no clear monotonicity either. I mean, if you add an extra point, what happens with this term is not at all clear. So. Anyway, yeah, so that's one problem that's interesting. We don't know really how to do it. But the other question Okay, so that was the assumption on beta. The other assumption was on the curve itself. So what happens if you don't have a Weil-Petersson curve? Fair question. Of course, there are many ways in which a curve cannot be Weil-Petersson, but maybe the simplest one, in some sense, is if it has a corner. This is not so easy to see from this Grunsky expression, but it's clear from this expression in terms of the Dirichlet integrals. If you think a little bit about how the conformal map will behave near a corner, you take the log derivative, it will be you have a singularity. So what happens? But still our identity holds, right? So this we have this truncated identity for the Coulomb gas, finite n gas. So it must be the case that this truncated Grunsky determinant diverges as n goes to infinity, and you could ask, is that possible to say anything about the rate at which it diverges? Does that carry any geometric information? And the answer is yes. So here's the theorem. So here we have to make, besides having corners, we have a strong assumption. So gamma is assumed to be piecewise analytic now. It could be a polygon, for instance. And I have m corners with prescribed interior angles, pi alpha p. Then the result is that the corresponding quantity that converged towards the Loewner energy in the Weil-Petersson setting now renormalized by log n. So this is the correct divergence, converges to this number on the right hand side. Only depends on the corner. And so I know some of you have seen such numbers before. So this kind of what's called a corner anomaly or whatever appears, for instance, if you look at how the heat trace behaves, also in the presence of corners, conical singularities. There's a lot of work by various people on this. But here it arises in a very different way. Here it's really coming from the asymptotics of the Grunsky matrix. So it's very different somehow from all the results. And one interesting problem that we are currently working out is here you see this theorem would not be able to distinguish between a square and a square where I wiggle a little bit the sides, right? It just sees the corners, right? So you would like to, it seems plausible that there is some kind of order 1 term that would somehow describe these how wiggly these sides are, maybe something about the interactions between corners. This is something we are working on.
So this one is for which beta? It's for v equals infinity?
Beta equal 2. Okay. Always 2, yeah. Actually, that's a good yeah. What happens for general? Yeah, that's right. So the proof, I won't really go into it, but it's really based on this identity involving the Grunsky determinant. And then it's a very careful analysis of essentially of the Grunsky coefficients in some sense, or this Grunsky operator. You have to somehow localize the contribution to the corners, and then this is a little bit similar to how these stories in Coulomb 1 are done, but you somehow introduce some sort of operator that more corresponds to a wedge. Then one has to check that also for this so log n contribution, there is no interaction between the corners. But it's really the key thing is the Grunsky story. All right. Good. Maybe I will skip this, but you can also, well, okay. I'll say something. You can do similar techniques. You can compute, for example, the exact growth of the Loewner energy of equipotentials as you approximate. This is somehow a little bit easier to compute. Okay, but now let me go to the second part. And I will leave the setting of a Jordan domain and talk about Jordan arc. Move to a sort of one-dimensional setting. As we will see, the Grunsky operator or some cousin of the Grunsky operator will play a role here as well. Okay, so here the setting is like basically the same as before, but my prescribed set now is not a Jordan domain, but it's just a Jordan arc. So it's like a piece of wire that's connecting, let's say, -1 to 1. And I'm interested in, I assume it's rectifiable. I consider a Coulomb gas of particles confined to my gamma. And then the partition function is like before, but here I'm integrating against arc length measures. All right, and I ask myself the same question: how does the free energy depend on the shape of this piece of string or piece of wire? Infinity, and I will also talk a little bit about, I didn't talk at all in the previous problem about the probability measure on points, but here I will talk a little bit about that. So, right, so there is an intermediate problem that I'm kind of skipping over that I will return to, and that's the one of a Jordan curve. Why would you skip over that? This, in the case of a Jordan curve, has in this context, has a very long history. I mean, in the special case of the circle, there's this Sager limit theorems, which could be viewed as a sort of special case of studying a Coulomb gas on the circle. There is the work I mentioned of Pomerenke, about Fekete points, which could be viewed as a version of this at beta equals plus infinity. Then anyway, the points are on the boundary, so it's really also a sort of one-dimensional problem. Then in Kurt's thesis, actually, he studied this Sager-Limit theorem problem for a bit more general curves, actually. But these general curves were also a little bit considered in there's a monograph by Sager in the 30s. And then in 21, where he, for the first time, made this connection in the case of a Jordan curve to the level energy, and this was extended to general beta by Clara and Kurt. So these works, I will come back to this and somehow explain why you have to do something different for the Jordan arc, even though it seems very similar.
So with curve, you mean a closed curve?
Yes, Jordan curve, exactly, yeah. Just, yeah, that's right. Homomorphic image of the circle, yes, very good. But, okay. So in the case of the arc, here, at least in the case when you have just the straight line segment, then this integral actually has a name. It's called the Selberg integral. And people have computed, there are asymptotic formulas expressed in sort of special functions and so on. So that's, to some extent, well understood. Besides that, there's basically only one paper. I mean, there's a paper by Widom from '69 where he studies Sager type problem, but in the special case when gamma is a circular arc. There's a lot of symmetries. He somehow managed to compute by some kind of black magic. There's some follow-up work on this by Stouts, my colleague at KPH, but there's basically none. And for general Jordan arc, there's almost no there's essentially no prior result. Okay, so let me state the result. And actually, to give the statement, what I'm going to do is I will associate to my Jordan arc a Jordan curve. And how do I do it? Well, so the green guy here is my Jordan arc. So this is what I start with. then I will sort of cut this open in the following way. So I consider this c plus root c squared minus 1, and I take the branch cut along gamma. Then this guy will map, actually, one way to think about it will map the complement of gamma in the sphere conformally onto the complement of a Jordan curve. That's the eta I drew. Another way to think about this is that you could say, well, I consider the sphere, I sort of cut it open. I have two copies of the sphere, each with gamma drawn on it. I cut open the sphere along this gamma. I open up and then I sort of glue them together, but kind of with the opposite side matched. Okay, then I get, then I uniformize. I get an abstract Riemann surface which I can uniformize, and then this sort of where I sew them together, the welding curve will be my eta, which will turn out to have this symmetry that as sets, it's symmetric with respect to sort of reflection. Okay, so that's something you can do, and well, I can check that, for instance, if my curve gamma is smooth, also eta will be smooth. So it won't really ruin anything in terms of smoothness. Okay, then I will associate the following number to gamma. So you remember we had the Loewner energy in the previous part. The Loewner energy is a priori defined for a Jordan curve. Right? So I compute the Loewner energy of this opened up curve, so the eta. Okay? So definitely, you can believe this, that if gamma is smooth enough, the eta will be smooth enough, it will have some finite energy. Okay? I take half the Loewner energy, but then I subtract something. I subtract 3 times the log of the derivative of the map that uniformizes the exterior of my eta curve to the exterior of the disk. This is the covariance curve. I look at this derivative at -1 and 1. This, of course, requires some regularity to make sense, but let's just assume that everything is smooth. Okay, so that's some number you can associate with your curve gamma. Actually, it's not a priori obvious that this is even positive or non-negative, but this you can check. It's actually a non-negative number, and it's 0 if and only if you started with the line segment. Then the theorem, one theorem is that similar setup as before. I look at this kind of relative free energy. I compare the partition function with my Jordan arc gamma with that of the straight line segment. And then I have this little bar, I didn't explain, but this is just, I've just divided away basically the 2 times the capacity to the power n squared. That's the normalization.
What better?
Say
What is better?
Well, here beta is 2, but here beta is general.
Thank you.
Yeah, so here you see, I will focus when I explain this. Okay. So beta equals 2, this is 0, so you just see this guy. This is kind of the analog of the result I explained before. But then we see this, I didn't say what is this JF. So this is some quantity which is analogous to this kind of Fekete-Pomerenke energy that I talked about before, that came from the harmonic extension of the log of the derivative of the uniformizing map. But here it's a little bit more complicated. There's some interaction between the endpoints, and there's some... and definitely some of you will recognize this, this number. Right? This is some number that also appears in SME stories, CFT. Okay. So let me talk a little bit about the proof, or what sort of goes into this. And maybe the first step is to explain what doesn't work. So I think initially we thought that this problem, okay, as I mentioned, the case of a Jordan curve, I would say is fairly well understood. It has been studied for a long time. And you know, how much farther can it be? It's just an R. I mean, it seems, and so how do you, what's the sort of starting point of the argument for a Jordan curve? Well, then the idea is that you transplant the problem with the exterior conformal map to the unit circle. And the exterior conformal map, this is good to have at the back of your mind, this sort of electrostatics background, because the exterior conformal, I mean, the equilibrium measure is just harmonic measure seen from infinity, right? So this transplants to just the uniform measure on the circle. So this somehow indicates from the start that the exterior conformal map is the good way to change coordinates. You could use the inside conformal map, but then you get some extra potential, right? It becomes more complicated. But so you do this, you transplant your thing to the exterior disk, to the circle, unit circle. So then my zk's here are points on the unit circle. Right? And then I just show here that this, this sum of the logs, which is what gives me the, there's also this Jacobian part, but this I can sort of split like this. It's just elementary rewrite. And then the first term would just be the corresponding weight on the circle. That would just correspond to a Coulomb gas on the circle, which is very well understood. The last guy is just the n, I mean the n squared of those guys, the n of those. So this would just correspond to a kind of linear statistics, which is, so the first and last term together, they are very well understood. This is basically setting for classical Sega theorem. But then there's this middle guy, which in principle could cause problem because they are sort of order n squared of those guys. So it's not so clear like whether it will dominate the last guy. But then at the end of the day, there's lots of cancellations and they have contributions of the same order. But you can also see here that this is precisely the kind of expression that I had in my Grunsky definition. This is like the real part of the Grunsky operator, at least for these points. So you can somehow see that the Grunsky appears in some way in this problem too, already here. Although there's no identity for this problem like we had for the Jordan domain. This is somehow very special. Okay, but anyway, if you try this, you try to use the exterior conformal map from your arc. You can still map, the complement of the arc is still a simply connected domain. You can map it to the complement of the disk. But you immediately run into two problems. I mean, for example, you will have each point on the arc will correspond now to 2 points on the circle. Okay, so that's some issue, and moreover, there's no clear. Maybe if you have some special arc, you could have some kind of symmetry, but of course, for a generic Jordan arc, there's no particular symmetry between the 2 points. So you will not get a nice model of the circle. That's easy to analyze. And anyway, even if you could get something, actually even if you manage to write something like that, the corresponding Grunsky operator, something has to happen, because the Grunsky operator is, the Loewner energy of the complement of an arc is infinite, because you have these corners of only 2 pi. So there's somehow something difficult. But, and anyway, you somehow feel that, well, it's a bit strange to try to use the circle as reference domain. This is somehow very different from the arc. Maybe it's more natural to just use a kind of straight line segment or something like that. But then it's not so clear how to use the conformal map anymore. So you run into these problems. But the key observation now is that the conformal map, it does several things for you simultaneously in the case of the Jordan curve. So it provides, of course, the conformal map from the exterior of the curve to the exterior of the circle. That's great. But another thing it does for you is to parameterize the curve by the electrostatic equilibrium measure, also known as harmonic measure, seen from infinity. And this property, the second property, is the correct one to generalize to this property. It's not the mapping property. So what to do? So we are going to do the following. So we are going to basically parameterize our arc by the equilibrium measure. And the way I want to do it is as follows. So I have my straight line segment. So I want to parameterize my arc by the line segment, -1 to 1. So I go t units from -1, and then I look at this pink part. I look at what is its harmonic measure seen from infinity. So what's the probability that the Brownian motion started from infinity hits this pink part? Well, if you compute, you get exactly this integral on the right here. And then what I'm going to do is I will go to a point C, sub E of t, here on the right, where the harmonic measure seen from infinity in the complement of the arc equals that. Just parameterize like that. Okay, so what does it? This gives me a complex valued function defined on the interval -1 to 1 that traces out my arc. And then I will sort of make a similar construction as before. I will also consider this log of this difference ratio. Now, for this problem, actually, this is also something that is somehow more. I mean, it's enough to take the real part. There's no additional information somehow in computing the imaginary, which is it's a difference from the other problem. So you make an expansion of this. So here you shouldn't expand in sort of Fourier basis anymore. You should expand in Chebyshev polynomials. These are the orthogonal polynomials for the line segment for this weight, for this harmonic measure. Okay, so you can do that. And the fact that you have just constituted guys here, this has to do with that we are using exactly this parameterization. This is somewhat important, that is, it is the equilibrium parameterization. Okay, so I have coefficients, AKLs. We call them the arc Grunsky coefficient. And so we do the same thing as before. We collect them in a semi-infinite matrix. We think of this now again as acting on little L2. Then there's a lemma here. If gamma, if my arc is sufficiently smooth, then, well, in the previous Jordan curve setting, you could say that this is a contraction. Here, the statement is slightly different. There's a symmetry which is, at least we don't know. In the case of a Jordan curve, these, well, there's some okay, let me not go into it. There's some additional symmetry which is not present here, but all the eigenvalues are strictly bounded below by minus kappa, where kappa is strictly smaller than 1. This is the corresponding statement here. We don't have a two-sided bound. Okay. And also a space line. And here, okay, so here we don't know what is the optimal regularity for this. This is an interesting problem. So we prove this under the assumption that gamma is C5. But basically just estimating the decay of these guys. So we could speculate that maybe there's a nice condition for like a Weld-Peterson arc or something like that, or like quasi-arc. So then the first statement is that, well, if gamma is good enough, so in the case when beta, now I just give the statement for beta equals 2, this, you have this limiting statement, and on the right-hand side you have also this Fredrik determinant, but for this arc Grunsky operator. So this result, in some sense, can be proved kind of on the Fourier side or on the Chebyshev side, but then it's actually sort of hard work to figure out this identity between this Fredrik determinant on the right and this. Remember, I had this Loewner energy, half the Loewner energy of the open curve minus 3 times this covariance term. So this is a separate result. For this, this first one can be proved on the assumption that gamma is C11 plus epsilon or something like that. But for the second result, we clearly not optimal. We assume that gamma is analytic. This simplifies. To get to optimal regularity, one has to. Yeah, so how do you do it? Well, with the setup I explained, with this equilibrium parameterization, the Grunsky operator, and these various estimates that we prove about it, you sort of set it up so that you can now employ a similar strategy as for the Jordan arc, but to prove the first result. It still requires a lot of work, but still somewhat similar, that you really view the map your gas back to the line segment, and then treat it as a sort of perturbation of sort of pure gas on the line segment. And there you can sort of go to the circle because you have a symmetry. And then for the second theorem, one computes the variations of both sides, basically check that they agree. But this is actually, especially the right-hand side is not so tricky because you have sort of geometric things, but here you really start with this Grunsky operator. And one very convenient tool in the case of a Jordan curve is that this Grunsky operator can be realized as an operator acting on some reproducing kernel Hilbert space of Lyman space. And this kind of stuff is not available here, at least that we know of. There's a lot less structure in this problem. Makes it a bit harder to deal with. Even from the even like classical electrostatic, I mean, like this Fredholm eigenvalues and things like this are not really understood, actually, in the case of an arc. There's a reason also that historically people haven't looked at it. It's just a much harder problem. But actually very interesting. People should look at it. Anyway, so here are some remarks. So we can maybe just compare the second statement here with the one we had for the Loewner energy and the classical Grunsky. So it's completely analogous. Yeah, as I said, I think that's an interesting problem on its own to study this Grunsky operator and its relation to the geometry of the arc. Maybe I will just flash the last slide. So we also studied the probability measure. I prove a result about the linear statistics here. This is also under some smoothness assumptions on the test function u and the arc. But basically what this says is that so here, this d is the Dirichlet integral of the harmonic extension of the function u into the complement of the arc. That's bounded at. So this somehow says that the fluctuations of the empirical measures, of these points as n goes to infinity converge to the Gaussian field of the arc. And this was for beta equals 2. There's a result for other beta. Then you have like a correction to the mean. That's a bit complicated to describe. Yeah. And this is a similar statement for the Jordan curve. Okay, thank you so much for listening.